In today's lecture, we are going to finish off this little subsection on series. Now, we've got about maybe one or two more lectures on section 4, but we've been working our way through these sort of ideas on series. And these last two sections are what we're going to talk about today. The Leibniz test. Up until now, we've been looking at series with positive or non-negative terms. So when you add sort of things together, we're always adding a positive thing to our series or our partial sum. A good question is, what about a series like the following that has positive and negative terms? None of the ideas that we've looked at so far can really handle something like that. Now, this kind of series here is known as an alternating series because the sign just flips around. Now, if you don't have that positive, negative, or negative, positive, it's not an alternating series. The sign does have to change every sort of, with every term you move to. So it can't be plus, plus, and then minus, minus. It's got to be plus, minus, or minus, plus, minus, plus. Let's have a look at Leibniz's alternating series test, or well, I just call it the AST for short. Now just suppose you have an alternating series. Here we've started the sum at little n equals 1, but I mean, you could just have it like this. Okay, where you start the sum doesn't really matter. That's why I don't put any detail in that sigma sign. It's just an infinite sum. It doesn't matter really where you start it. The alternating series test says if these three conditions down the bottom here are satisfied, then the alternating series converges. So these UNs are assumed to be all positive and decreasing, or I guess non-increasing if you want to use the inequality sign. And the U sub n converges to 0. Under those three conditions, Leibniz test, or the alternating series test, tells you that the alternating series must converge. So where does that come from? Well, I'm not going to prove it. I'll just give you a little outline of where it comes from. So with a lot of the proofs for these tests, it relies on working with a sequence of partial sums. And this one's even trickier because what you do is consider the sequence of partial sums with an even subscript. So what you do is you show the sequence of even partial sums, I guess, converges. And to do that, you use the monotone convergence theorem. And you also use 1 and 2. Okay, so those two conditions. Also show that if you have an odd subscript, then this sort of subsequence of partial sums also converges. And that uses this information down here. Now, both of those, that S sub 2n and the S sub 2n plus 1, actually converge to the same limit. Now that's just a real rough sketch, so don't worry too much. You would certainly never be asked to prove something like this, but what I'm trying to do with just these little sketches of proofs is to show you how a lot of this stuff relies on sequences and that monotone convergence theorem. Now it's a bit sad that the monotone convergence theorem actually isn't examinable, or you're never going to get tested on it, but we use it all the time in this section. So, but anyway, getting back to from a practical point of view, how do you use this test? That's the important information. Before we get to that though, Leibniz. Anyone heard of Leibniz? Yeah, a few people. One of the big contributors to early development of calculus, and apart from wearing funny wigs, he also has a university named after him in Hanover, in Germany. So you know you're doing pretty good if you have a university named after you. All right, let's have a look at how we can use this, the AST or Leibniz test. Consider the following series. We're asked to discuss, we're asked to show that this series converges. So how do you do it? Well, the obvious idea here is to show all the conditions of the AST or Leibniz test actually hold. So let's actually go through and do this. So let's identify some of our parts. U sub n is just 1 on n here. So let's look back. I'll put this back up in a second. We've got 3 things to check. The U sub n's are all positive, they're non-increasing, and they converge to 0. That's the 3 things we want to check here. So all we do is just tick them off our list. All right, so the first little condition here is all the UNs are positive. So that's certainly true for 1 on n. 1 on n is positive for n greater than or equal to 1, so that's easy. What's the second part? We want to show that this little sequence is non-increasing. Now, 1 on n is greater than or equal to 1 on n plus 1. Okay, you don't have to prove that, it's pretty obvious. So we're happy with that. So that's the second part of Leibniz or AST's condition satisfied. And the third one, we just want to show that the UNs go to 0 as n goes to infinity. So as n gets large and positive, this is going to get small, or it will tend to 0. So all the conditions of our alternating series test hold, and we conclude that our series up here, our starred series, converges. Easy. That would be perfectly fine for end session test. You've labelled everything's labelled nicely, set out, we've ticked off each 3 things. You don't have to go and do an elaborate proof, especially in part 2. You certainly wouldn't need to show induction there for this particular example anyway. Now, let's just go back a second. I'll remove this in a second. What happens if one of these conditions don't hold? If I have, say, an alternating series, and I can only get 2 of those 3 conditions to hold, what does it say about our series? It says nothing, right? It might converge, it might diverge. We can't use the test. Many times what will happen is you're given some series, you'll try to apply a bunch of different tests to it. They won't all work. They won't get you what you want. So part of it is not giving up, and also being wise about the initial choice of test. Any questions for that example? Any questions? Yes?
How do you go about choosing your U sub n?
Oh, good question. Well, the U sub n's there. The U sub n is one, so the 1 on n comes from there. Okay? Because the original setup is always something like -1 to the n times U sub n. You with me? Yeah. So you don't have to choose anything in this case. Any other questions? Okay. Let's do another one. Now, there's a smart way and a not so smart way to do this question, just like a lot of questions on series. Huh? What? The smart way. Well, the smart way for me to do this series. Well, no, I want to hear from you. What's there's a smart way and no, someone else. I know you know the smart way. I know you know it as well. Someone else. People see this and they go, oh, it's an alternating series test. It's even simpler than that. It's even simpler than that. Can anyone see it? It's a special kind of series that you would have seen at school. It's a geometric series. Okay? So, as a little side note, we can write it like this. But we can also write it like this. Oh. Now, this question, it's not poorly chosen, because both tests are okay. It's just a simple example. The underlying theme here is that in many cases you can apply more than one test to a series. It's up to you which is the most efficient, which is the least time consuming. Okay, so firstly note, a geometric series and -1/2 is strictly between -1 and 1. So we know this series has got to converge. Now that would be the smart way to do this, to do this problem. But let's actually see how we can apply the alternating series test. The thing is, it's a simple series, so let's actually try to apply what we've just learnt to this. Oops. So if I was in an exam, I'd stop after the first solution. That's it. It's perfect. You know absolutely everything about that series. Not only know it converges, you know the value of the series, which is rare. So in this case, in the second case, u sub n is 1 on 2 to the n. So all we need to do, and I'll take this away in a sec, is check that these three things hold. Okay, so firstly, for each n, say greater than or equal to 0, are our u sub n's positive? Yep. Okay, the second part of Leibniz rule or Leibniz test says we need to have a decreasing or non-increasing sequence. So this is bigger than that. So we can get the inequality we need here. And the last thing is that u sub n has to go to 0. Let's check that. So 1 on 2 to the n, as n gets large and positive, that's going to go to 0. So our conclusion is that all the conditions of the alternating series test hold. And our original series star must converge. Now, important, you cannot use the AST to show a series diverges. You can't do it. So don't try, okay? You need some other test. Questions? So if you can remember these three things, you're doing well. And show that they apply, okay? Now, we've seen some series converge, some series diverge. In the previous example, we showed this series converged, right? Now, there is another kind of convergence called absolute convergence, where all you do is you stick an absolute value in your sum or your series and see what happens to that series. The reason we can do this is because this sort of convergence with the absolute values, it brings really good things. Look at a simple example that I've boxed up there. If I put absolute values in here, the minus 1 to the n is going to disappear, and I get this series. Now, this is another geometric, I guess, series that also converges. We know this guy converges and this guy converges. So we would say, since this converges, that this original series converges absolutely. Now we're going to see why that's important in a minute, but just bear with me for a second. Now this is a strange, well not a strange example, but don't be fooled. This series converges, this series also converges. All we're really interested in is the convergence of this series. We don't really care about that for this particular example. All we're saying is that this series converges absolutely. So if you chuck some absolute value signs in there, the new series converges. So let me show you sort of a converse here. Suppose we have this series. Let's put some absolute value signs in there and see what happens. If we put an absolute value sign in this series, the minus 1 to the n just becomes 1. And what's this series? Well, it must diverge. It's a p series, right? It's a p series with p equals 1 that diverges. So what can we say about our original series? The series in this case does not converge. Absolutely. Now let me give you an example of how these absolute signs can help you out. How they can make things easier for you when you're tackling series. Now this theorem here, the absolute convergence test, is huge. It's really useful. It's really useful. So basically it says if you put, let's say this is your original series here, and you put some absolute value signs in there, and that new series converges. If that new series converges, then the original series has also got to converge. Now the proof for that's a bit tricky. I'll come back to that in a second. Let me show you how to apply this result first. All right, I'll come back to the proof if we have time for that. All right. Let's have a think about how we can look at this new series and use that past test to help us out here. I'm going to let a sub n equals sign on n squared, and then I'm going to put some absolute value signs in there. So consider, please. This series here with the absolute value signs in it. Does it converge? And if so, why? Any ideas on how you might show that sigma absolute sin n on n squared converges? Well, let's compare sin n with something. Correct. Now this is an important inequality that you can use to your advantage. If I divide both sides by something that's positive, I can come up with this inequality. Okay, you don't need the absolute around the n squared, it's all positive. Now, what do I know? What do I know about sigma 1 on n squared? It's a p series. It's a convergent p series. So, what can I say about my original series? Well, it's a convergent p series. So what can I say about this series here? It's also got to converge by the comparison test. Not the limit form, just the regular comparison test where you have inequalities. So, our sigma with the absolute value signs in it converges by the comparison test. What does that mean about our starred series? Well, we can say that the starred series converges absolutely. And what does that mean? Well, let's go back to our, I'll put this back up in a sec. Let's go back here. If this converges, then the original series converges. We've just shown that this converges for our particular A sub n. Now, there's a lot in that solution because it relies on ideas from previous lectures, in particular, the lecture from yesterday, the comparison theorem or the comparison test. So I'm not expecting you to really look through that solution and follow every little detail. If you can, great. But so we're kind of using a test within a test there. That's what makes it a little bit hard.